All right, this is the intro video for AP Calculus AB section 7.1. We're going to be looking at the area of a region between two curves. So we have looked in the past at the area under a curve, or maybe the area between a curve and the x-axis, but we have yet to combine two curves together and find the area between them. So the formula is going to be this right here. Area is equal to the integral from a to b of f of x minus g of x dx. So some things to think about here. Number one, for this to work, f of x needs to be greater than or equal to g of x on the interval a to b. In other words, f of x will be the higher function, is the word we'll use for the moment, on AB, so it'll be higher. So if we look at a graph, it could look something like this, where this would be f of x, and maybe g of x would be down below it somewhere, perhaps like that. And we could cut that region off, say, here and here, maybe that's A and B. We could then find this area between those two curves. And let's talk a little bit about why that formula up here is what it is. Remember that from way back that a definite integral is simply an infinite summation of really skinny rectangles. And so if we're trying to find area, inside the integrand is going to be the area formula for a rectangle. The dx is the base, and f of x minus g of x is the height. I'll show you that on the picture here. So down here, if I were to draw in a representative rectangle between these two curves, the dx is right here. The dx is the width or the base length. It's just a small change in x. And then as far as the height goes, the distance from the red curve down to the x-axis, that would be f of x. And then the distance from the blue curve to the x-axis, that would be a height of g of x. So to find the height of the rectangle, we would just take the higher height minus the lower height, and that would allow us to find the distance between them, also known as the height. So just keep in mind that when we find area, it's really, in its most simplistic sense, is going to be the integral of height times base, which is, of course, just the area formula for a rectangle. Okay, so we need to explore a little bit more in this, so let's take a look at the lower part of our page. So I think a legitimate question here is this one here. How does this work for functions that fall below the x-axis? So let's focus on that for a minute. So if I've got f of x, and let's say that f of x, I don't know, f of x does a bunch of stuff. Let's say it does that, and g of x is mostly below. Maybe there's some parts above, but whatever. There's g of x. Let's say that the region that we care about is from maybe here out to here. How does this work out if we have parts that are above and or below? We'd be looking at this area here. That would be our goal if we were trying to find the area between those two curves. So how does this work out for a representative rectangle? So I'm going to look at a couple cases here. So if we have both curves under the x-axis, according to the formula, we're supposed to go high function minus low function. So I want you to think about this. For the red function right here, the y value might be, well, let's just say it's like -2. And for the blue function right there, if the red function's at -2, maybe this would be like -5. So if I think about high minus low for the height, high minus low would be -2 minus -5, which is really +5, that's 3. And I think, just drawing the rectangle there, you can see that it's going to be 3. Just by going high minus low, you get the correct height. So in other words, when both functions are below the x-axis, the formula holds true. We don't have to make any special adjustments. And then if you have one function above and the other function below, I think we'll find that this still holds true. So the y value there would maybe be like 7, and the y value for the blue graph right here would be maybe -6. So if we think about how that would work, we would go high minus low. That's really plus, and so a distance of 13 makes sense, right? 7 above, 6 below. The full height would be 13. Of course, it works for stretches like this, like we showed earlier, and then this is similar where we got a high and a low, or above and a below, excuse me. And so the broader point here is simply that formula, integral of f of x minus g of x, or integral of high minus low, is going to work regardless of the location of the functions, whether they be above the x-axis or below, or some combination thereof. I just want to reiterate that practicing using a representative rectangle to help us visualize things is pretty useful now. I think in the coming days it'll become even more useful. So get into the practice of drawing that out graphically just so you can kind of get a picture of what's happening. All right, we're going to do one example on your next page. Okay, so for this example, it's going to be no calculator, and we're going to be finding the area of the region bounded by all those graphs. And so the first thing we're going to attempt to do is to graph those graphs. So it's going to look something like this. Y equals x squared plus 2 is a parabola shifted up 2. And represent it with about something like that. Y equals negative x. There's just a line, a y-intercept of 0, negative 1 slope. And then x equals 0 and x equals 1 are both vertical lines. And so one of them's at 0. We'll put that right there on the, let me do a little better job with that. Put that right there on the y-axis. And then x equals 1 would be over here somewhere. And so what we've done now is we've defined our region. So our region does look something like that gray region. I'm going to erase all that gray stuff, but that's the region we're going to try to find the area of. So what I'm going to do now is I'm going to write in a representative rectangle. I'll just put it out here in the middle somewhere. And I'm going to try to calculate the area. Again, keeping in mind that this is a no calculator question. So area equals integral from where to where. Let's start with that. So we're going to be accumulating these rectangles, and we're going to be accumulating them from left to right. Probably another important thing for us to note, to think about here, is with this rectangle, let's think about, is this rectangle going to be dx wide or dy wide? And by width, I'm talking about, in this case, the horizontal measurement, the thickness of it, I guess, if you will. And we would say that this is a dx wide rectangle because the thickness is measured horizontally. It's measured on the x-axis. Okay, so anyways, if we have a dx rectangle, we'll always be accumulating from left to right, like this. And so let's think about where I'm going to start accumulating for my region. I'm going to start accumulating when x is 0. And I will stop accumulating when I get to the right edge over there. That's when x is 1. So it's going to be the integral from 0 to 1. And then for my region, I'm going to think of the height of my representative rectangle as high minus low. So the high function is x squared plus 2 minus the low function, which is negative x. And then my base length, or my thickness of my rectangle, is dx. So do a little bit of cleanup work here. Integral from 0 to 1 of x squared plus x plus 2 dx. And now I'm ready to evaluate this and actually find the area. So I'm going to do my antiderivative first. It would be 1/3 x cubed plus 1/2 x squared plus 2x. All of that evaluated from 0 to 1. And I'm going to use FTC1 to help me out here. So it's going to be 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1. And then, it doesn't always work out this way. It's kind of nice though. With the 0 in there, it just ends up being 0 plus 0 plus 0. Okay, then over here, we clean it up a little bit. It's going to be 1/3 plus 1/2 plus 2. The common denominator is going to be 6. So 2/6 and 3/6 is 5/6. I think it's going to be 17/6 for final answer. Let me do a better job with my 17 there. And that's it. That's going to be the area. It's the exact area. It's not any kind of an estimate. Wow, there we go. 6. It's the exact area between those two curves on the interval from 0 to 1. So when you come to class, we will look at a few more of these and add a little complexity to it, but that's the basic plot. Make sure you know how to do this when you come to class. See you then.